So welcome back from spring break. This is lecture, I guess, number 15 here. And before break, ancient history, you probably have forgotten, just like I did, but we talked about basically an overview of the field of optimization. And then we talked about convex sets and functions, which are needed to basically specify one particular class of optimization problems that's particularly relevant for DER problems. And so that's convex optimization. So today's lecture, we will talk about how we specify convex optimization problems and how we use software and algorithms in order to solve them on computers. Okay, but before we get into this, I just want to talk about the midterm briefly. So the week before spring break, you guys took your midterm exam. It was a 24-hour take home. And just a couple of comments about that. So first, I think that the grade breakdown that I had in the syllabus was 20% homework, 30% midterm, and then 50% for your final project. So the first thing I want to say is, 70% of the class is stuff other than the midterm. So even if the midterm didn't go exactly how you wanted it to go, there's still plenty of opportunity to get a reasonable or even an excellent grade in the class. The second thing is that this was my first time giving a take-home exam in a hybrid class that has both a purely online section, but also an in-person section. Things would be much simpler, I think, for everyone involved if I could just give an in-class kind of 1-hour midterm exam, something like that. It would be shorter, it probably would be easier, and it would be a better test of like what's actually in your brains rather than what you can rack your brain and use other tools potentially to do in a 24-hour period. So different skills being tested. I guess they both have value. But I think next year I will do the exam a little bit differently. So this year, the rule basically was only use class materials. So lecture slides, your own notes, homeworks, and things like that. And I specifically, I didn't say explicitly, but what was implied by that is it's not okay to use ChatGPT or other generative AI type tools, right? And I don't love that because first of all, I don't want to have to police that. Like it's very clear from this exam, by the way, there were some distinctive errors that were made by AI tools that were replicated in a lot of students' solutions. So it was clear that some students did use generative AI for certain questions. And I don't want to like have to police that. I don't think that would be fun for me or for you. I don't think it would be really productive for anybody. So I'm not going to do that. So I think next year, what I will do is just say it's okay to use whatever tools you want. Probably we'll still have to take the test individually. But other than that, asking other people is off limits, but anything else basically is cool. So you can use ChatGPT, you can use Perplexity, you can use whatever tool it is that you may like. But so for this exam, ChatGPT, we ran the exam through ChatGPT and it got about a 70%, something like that. So if a low C is acceptable, like if that's kind of what you're going for, then I guess you can sort of uncritically just copy and paste ChatGPT solutions and it's fine. If you're going for a deeper level of understanding or for a higher grade, I guess more pragmatically, then it probably makes sense to not use or not only use AI supportive tools. And by the way, I'm not trying to look at anyone in particular here. I'm trying to move my focus around the room because I'm not accusing anybody, and also it's perfectly fine. So I like that approach of saying you can use the AI tools if you want to, but just recognize that because of the way that generative AI tools are trained, and we'll learn a little bit about AI stuff in a couple of weeks here. Not a lot. We'll kind of scratch the surface as we do with various things. But the basic for how these models are trained is engineers, companies gather huge data sets. They scrape the internet. They use the text of books, textbooks, homework solutions from Chegg and whatever else, whatever they can get their hands on, basically. And then all that training data is fed into a machine learning model, which basically calibrates parameters within a function, a mathematical function, that is meant to sort of replicate the input-output behavior of the data set that it's given. So roughly what that means is like the more data that there is and the more correct the training data are, the examples that are pulled from Wikipedia or people's uploaded homework solutions or whatever it might be, the more accurate those tools are likely to be, which basically means they're good at solving easy problems. But as you get further in your studies, your undergraduate studies or into grad school, the problems you study tend to get more and more specific. So fewer and fewer people have worked on them other than you. And also they tend to get harder and harder. So that basically means that the training data examples that are available for the machine learning models that we can use to help solve these problems get sort of further and further from the real problem that we actually want to solve. And so that roughly means that as the problems get more challenging, the reliability of these tools goes down. And so if you are going to use ChatGPT or Claude or some other model to help out with assignments, or more pragmatically to help out with real engineering tasks after you get a job, you should be careful, right? If you're studying something subtle, something challenging, something that not many people have probably tackled before, then you should be very careful because at least the current generation of these tools essentially give you the same level of perceived confidence in the solution, whether it's adding 2 + 2 or solving some really hard problem, right? And so they don't tell you, oh, this output is trustworthy or not, at least the ones that I'm familiar with today. Now, a new generation of tools later on in a few years may do that. I think that would be a good innovation to build in. But anyway, I don't want to say too much more about this other than if you use AI tools to solve engineering problems, especially if you go into a job later and there may be safety issues involved in the problem solving, it's very important to use your own intuition and your own knowledge to basically check what the AI tools generate. And last point is that oftentimes checking the correctness of the AI output is about as hard as just solving the problem yourself. Okay, so that is all. Yeah, we're not going to go after people who use AI. I think that's perfectly fine. And I think the workflow we'll do next year with letting people use AI tools, but just cautioning them that the results, the outputs aren't necessarily trustworthy, is a better reflection of how people actually solve problems today anyway, right? So in some sense, we'd be grading you on basically what you would do in a real job with the resources that are available to you. Okay, so that is all. I think the last thing about the exam is that I may just tune down the weight on the exam a little bit. So rather than a 30-20 split between the exam and homework, I might go 25-25. So we have one more homework assignment. You guys have already kind of gotten all your homework points except for that last one. So we'll bump the weight on that a little bit, bump down the weight a little bit on the exam. Does that sound okay to you guys? All right, and then the project will remain half the grade. So that really is the big piece that's remaining in the class. And the project really is our focus. So we have roughly a month between today's lecture and the first students beginning to present their final project stuff. So you guys should be working really hard with your teams on project stuff. That's almost exclusively the work for this class for the next month or so. So any questions about exam stuff or course logistics, anything else?
One question.
Yes.
Someone before spring break mentioned like redoing the exam for partial credit. Any thoughts towards that?
Yeah, it's a nice suggestion and I like it in principle, but I think due to the technology issues that we're kind of dealing with uploading grades on Gradescope and things like that, I think that it's probably not going to be feasible this semester. So sorry about that, but I guess I would just say work hard on the project, deliver something cool that we can all get excited about, and I think your grades will be fine. The last thing I'll mention is that I think we actually will curve the final grade of the class. So we're not going to curve the exam grade, but at the end of the semester, we'll probably bump people up to some degree, a few percent, something like that. Zach, did that address your question?
Yeah, okay. Thank you.
Okay, thanks.
A general question, because you mentioned to applying AI for real problems.
Yeah.
Do you think that companies do not allow employees to use AI tools for confidential issues?
So the question is, if you're working for, say, a software company, Google or something like that, would they not want you to use generative AI tools for confidentiality reasons?
Yeah. Do
Um,
you think is this
Potentially. So there typically is feedback. So if you use ChatGPT app or something like that, typically you have a login, and the stuff that you supply to ChatGPT is typically sent back to OpenAI and may be used in further refining and training of algorithms. So I think if you're at a big software company, I mean, I don't know, I don't work at Google, but I assume that they probably have their own in-house tools, and they may have specifically customized versions. So more specialized. So not a general purpose ChatGPT-like thing, but a thing that specifically helps Google employees write code more efficiently, something like that. Right. So I think if it's an in-house tool and if they control sort of information flow out of the tool, then probably it's fine. They may probably encourage people to use it if it improves productivity, right? And produces correct or trustworthy outputs. Yeah.
Because I was thinking, if we learn to use it right now, because all of us use AI for our research, everything,
Yeah.
and then you go to a company and they have like a rule, do not use it for confidential, it will be difficult for you to adapt in the new environment. So that's why I'm asking.
Yeah, I'll just paraphrase for folks online. So suppose you go to work for a smaller company that doesn't have maybe the resources to create their own internal versions of tools or something like that. Then they may ask you not to use one of the broad tools like ChatGPT for confidentiality reasons. They don't want to upload their code or their documents or whatever it might be to the tool. So you're saying that if you find yourself in that situation, and if in your educational career you have been using the tools a lot, then you may find yourself not as productive or capable or something like that on the job. It's a fair point. I don't know, like I'm an academic, so I don't have a lot of industry experience, so I can't say how common that situation is, but I agree with you. It's a risk to some degree. Yeah. Yep, good point. Thanks. Okay. Right. So I think we will jump into today's lecture again on actually how do we solve convex optimization problems. So we'll start out by talking about something called disciplined convex programming, which is basically an approach, a technological approach to modeling and solving convex optimization problems. We'll talk specifically about CVX, which is a toolbox in MATLAB. But if you prefer to work in Python, there is a toolbox, a similar version called CVX Pi. The syntax is slightly different, but under the hood, the algorithms and the capabilities of the software are broadly the same. And there are versions of CVX that you can find in the stats language R and the programming language Julia as well. So we'll talk about that. Then we'll go through a couple of examples. And then we will talk about under the hood, what does this modeling language, CVX, the basic tool, the basic role that this language plays is to take your problem specification and reformulate it into the structure that a solver wants, and then pass it to the solver, get back the solution, and transform it back into your kind of human readable form. So what is happening under the hood with the solvers that CVX passes to? We will talk a little bit about that in the third section here. Okay, so what is disciplined convex programming? Well, it's a framework basically for describing or specifying convex optimization problems. So disciplined convex programming, broadly speaking, typically uses a library of functions, typically called function atoms, that have labels or tags on them associated with curvature and monotonicity properties. So is it convex or concave? Is it increasing or decreasing? Things of that nature. And we talked in the last lecture before break about how we can use those curvature and monotonicity tags associated with functions and then do compositions of functions to take sort of simple atomic functions and put them together in complex and useful and interesting ways. And then those composition rules are basically encoded in the framework of disciplined convex programming. So the software uses those rules to basically certify or verify that your problem is convex and can be solved globally and in polynomial time. And so this set of tools basically is sufficient for certifying convexity, but not necessary. So what that means is if you take your problem, you run it through CVX and it says, cool, this is convex, I'm going to give you a solution. Then you have a positive certificate that your problem was convex. So in that sense, it can help you with sort of some of the modeling gymnastics that we talked about before break about, checking whether a set or a function is in fact convex. But it's not necessary. So what that means is that there are convex optimization problems that you can write down on paper that you can give to CVX, and it will say, I don't know what to do with this. This doesn't match any set of atomic functions or any composition rule that I know. And it'll just give you back an error, basically. And then the task really is up to the modeler, the user of the software, to figure out how to basically re-specify or reformulate your problem in such a way that CVX or another tool will accept it and give you a solution. Okay, so the basic problem structure that is used in discipline convex programming in MATLAB, Python, etc., is as follows. So we have an objective function that gives back a scalar. So just a number, not a vector or a matrix. And the objective can be either to minimize a convex function, to maximize a concave function, or if we're solving what's called a feasibility problem, you can omit the objective function and just put in the constraints, and CVX will return basically one feasible point, one point that solves your constraints. And those constraints can be either a convex function upper bounded by a concave function, and of course, a constant is a special case of either a concave, a convex, or an affine function. So this can be convex less than a number, or a concave function. And then vice versa, we can have concave greater than or equal to a convex function, basically the same thing here, just rewritten. Or we can have equality constraints. So this could be, for example, the dynamics that describe how the energy stored in a battery evolve over time. And those dynamics have to be affine. So an affine function basically just means linear plus a constant. So an ax plus b sort of a format. So this is, I would say, probably the most restrictive aspect of discipline convex programming is that things like dynamics, other equality constraints need to be linear. So if you try to program a nonlinear equation, you'll typically get an error. And then if your problem is unconstrained, then of course you can omit the constraints as well. And we talked about this before lecture or before break, but a function that is both convex and concave is an affine function. All right, so CVX is one implementation of discipline convex programming, and there are others in other languages and things like that. CVX is the MATLAB implementation. And so basically, as I mentioned, it takes the program or the problem that you specify, and it transforms it into a form that can be given to a solver, passes it to a solver, and then interprets the exit status from the solver, which could be everything was cool, it took me 30 seconds to solve your problem, and here is a certificate of optimality, something like that. Or it could say, sorry, there is no X that is feasible for all of your constraints, or it could be unbounded. And again, what this means is basically there is a direction within sort of the set of feasible solutions for your problem. There's a direction where if you just keep going in that direction indefinitely, the objective value keeps getting better and better and better. And so that means that you can, if you're in a minimization problem, you can make the objective function arbitrarily small, however small you want to go. And then again, we transform the solutions back into kind of the user specified form. So here's what the syntax looks like in MATLAB. So basically the MATLAB scope is delimited by a CVX begin tag here and then a CVX end tag here. And we specify the variables in our optimization, the things that we're trying to choose, the actions we're trying to take. And then we minimize an objective function. And then this line here, subject to, basically says the constraints follow after this line. And so here, very simple problem instance, basically, we might have a matrix A, which would be a constant, meaning it just has numbers in it. It's not a variable in the optimization problem. The right-hand side vector here, B, is another constant. X is a variable within the scope. And then when you run this code, whether it's in a function or a script, after the CVX scope ends, so your computer runs this thing, it executes all the transformations and solution that CVX does, the variable X would be populated with an optimal solution. So it would have numbers in it after the CVX thing runs. So here, this problem that we're looking at, maybe A is a wide matrix. So here, this would be a number of linear equations where the number of variables X is larger than the number of equations. So there might be infinitely many solutions to this AX equal B equation. And then among those solutions, we're looking for one that has the smallest norm measured in the Chebyshev or the infinity norm. So roughly, this is look for the smallest X that solves this set of linear equations. And then another important output is CVX status. This is a variable, and it will be a string. It'll either say solved, infeasible, or it could say something like infeasible or feasible but inaccurate, something like that. Or it might say unbounded. So it basically tells you about your problem instance. The indentation that showed up doesn't matter, so you don't have to move this in a little bit, but you can. It makes it a little more readable. And then this line subject to you can omit if you want to. And one thing that often trips up new users of CVX is that constraints use a double equal sign, which is sort of the check for equality of two things in MATLAB, not a single equal sign, which is assignment in MATLAB. That basically would say, take this number and store it in some variable. And then constraints are like x non-negative are interpreted element-wise. So if x is a vector of, say, 1,000,000 decision variables, this would mean that each of those elements of x has to be non-negative. And then I guess if you haven't really worked with optimization tools before, this is maybe not, it's not clear why this is an advantage, but a lot of solvers require you to specify an initial guess. So you say, here's my problem, and I think a pretty good starter solution might be this thing here. And they might even require that your initial guess is feasible, which means solving a feasibility problem, which can be actually quite challenging in and of itself. And oftentimes for algorithms, we may need derivatives of functions. So derivatives tell us basically what direction a function is increasing or decreasing in. So you can imagine how that would be useful when running an algorithm to try to minimize or maximize a function. So CVX actually doesn't require you to do any of that, which is kind of nice. If you have a complicated problem, it can actually be non-trivial to find derivatives of all your functions with respect to the decision variables. If your problem is infeasible and you pass it to CVX or CVX pi, the exit status will be infeasible, and they will populate x with a vector of nans. That means not a number. So then if you are trying to use this downstream of the CVX scope to, I don't know, draw a plot or something like that, you will not be able to plot anything because you'll have nans stored in your element. For an unbounded problem, CVX behavior is a little bit interesting, so it's important to be aware of this. So if your exit status is unbounded, again, that means that there's some direction in your feasible set, your set of feasible solutions where you can move forever, and the objective function just keeps getting better and better. So in that case, CVX returns a direction, the direction, or at least one of the directions in which you can move in order to arbitrarily improve your objective function. And so this thing x itself probably is not feasible, meaning it doesn't satisfy all of the constraints. But if you want to generate a feasible x tilde, so you could do that by omitting the objective function and then resolving the problem just as a feasibility problem with only constraints, no objective. So then you would get some x tilde that lies in your feasible set. And then if you start at that point x tilde and move in the direction x, scaled by any scalar alpha, any positive scalar alpha, then the objective function just keeps getting better and better. All right, so some examples of these kind of atomic functions that have, again, tags for curvature and monotonicity that we can use to build up more complex functions. So some examples that are useful that come up a lot in DER applications would be the max or the min function. So here x is a variable, a vector, an n-dimensional vector. So this just means take the largest component of that vector. So the max function is convex and non-decreasing. Which if you remember, if you take any convex function, you stick it into a convex non-decreasing function, then that composition of functions is convex. So convex non-decreasing functions are great in that sense. The min function is concave and non-decreasing. There's a function called pos, which means the positive part of x, and that's defined just as the max of 0 and x. And so here this would be interpreted element-wise. And we compare each element of x to 0, and we take the bigger. So that means if some element of x is negative, -3, -12, then the bigger of -12 and 0 would just be 0. And so this function returns 0. But if x is positive or 0, then it just gives you back exactly that component x. There's also the square pos function. So again, similar behavior, but now rather than giving back x sort of linearly, 1-to-1, we would give back x squared. So it would be a quadratic looking function. 1 over x is convex and non-increasing for values of x that are strictly positive, and we write that in a way. So if you just try to program 1 divide x, CVX probably will freak out. But if you specify that you want 1 over x and x is restricted to be positive, then you have kind of nice, consistent curvature, and CVX would be fine with that. The square root function norms. So any norm with a subscript p. So this could be the 1 norm, the 2 norm, the infinity norm, or actually you can take the 12 norm or the 9 norm. That all works with different values of p. And those are all convex functions. And then the sum of squares. So this comes up, for example, if you're solving like a data fitting type problem, oftentimes you will look at the sum of squared errors as your optimization criterion. And so that sum of square of x is, again, a convex function. A couple of examples here. So one that comes up pretty regularly is what's called a quadratic form. So who has heard that term before, quadratic form? Yes, about half the class, including one of our undergrads. So where did you learn about quadratic forms?
I don't know.
Just somewhere. Okay. Cool, you've heard it. Okay, great. Okay, so a quadratic form is a function of an n-dimensional vector x. And it's parameterized by a matrix, a square, an n by n matrix P. And it basically is the generalization of the function x squared or ax squared, px squared, I guess, of a scalar variable x to vector valued variables. And without loss of generality, you can always assume that the weight matrix here, P, is a symmetric n by n matrix, meaning P is equal to its own transpose. And there's a short proof of that. Basically, if you call a quadratic form with a matrix that is not symmetric, you can always replace it with this symmetric matrix here, P plus P transpose divided by 2. So the average of P and P transpose. And you can convince yourself that this thing is a symmetric matrix. I won't go through that, but it's not too hard to do. But you can show that if you take the weight matrix P and you replace it by the average of it itself and its transpose, then you actually get the same thing as you get from just taking x transpose px directly. By the way, this whole thing is a scalar. The result of a quadratic form is just a number. So x here is an n by 1 vector. P is n by n. So if we do n by n times n by 1, we get n by 1. And then x transpose is 1 by n. So if we do 1 by n times n by 1, we end up with a 1 by 1, or a scalar. Okay. All right, so we can basically factor out, distribute the x and the x transpose here, and we get the right-hand side. Because this number here is a scalar, it's a one-dimensional object, any number is equal to its own transpose. It's kind of a silly thing to do. What is the transpose of 12.7? Well, it's just 12.7. But it helps us with sometimes some mathematical manipulations here. So we can say this thing here is a scalar, so therefore it's equal to its own transpose. You may remember in lecture number 2 or something like that, we talked about some math background and transposes of matrices. So to distribute this transpose to each of the terms, we basically put a t, a transpose on everything, and then we invert the order. We reverse the order of things. So we would have an x transpose over here. P transpose, well, its own, P transpose gives us back P. And then we would have an x transpose on the right here. So anyway, now we have the same thing added up twice and then divided by 2. So we get back just the thing inside, the x transpose px. Okay. So this shows that whether you do this quadratic form or this quadratic form, you get back the same answer, the same number. So without loss of generality, if you have an asymmetric P, you can always replace it with sort of the symmetric version of P. That makes sense. So to do a quadratic form in CVX, we write quad form, the variable x here, and then P would be the weight matrix. Okay, so when is a quadratic form symmetric? When is a quadratic form a convex function of the variable x? So that gets into basically properties of matrices and square matrices in particular. So convexity basically has to do with the definiteness, which is kind of a generalization of non-negativity of the weight matrix. So for a scalar quadratic function, just a number times x squared, that is a convex function. It curves upward if the number we multiply x squared by is positive or 0, right? So it's convex in that case. And then if say, ax squared, if a is negative, then we have concave down or a concave function. So similar thing here. If the weight that we're multiplying by, right, this is kind of x transpose x would be x squared, roughly generalization. And then p is the generalization of the scalar that we multiply by. So if p is like positive, but in a matrix sense, then we get that our quadratic form is convex. And so the sort of generalization of positivity is what's called positive semi-definite. And actually, that would be the generalization of non-negativity to matrices. So this says if you can take any x, any vector x, and multiply x transpose px, and if the result of that is always non-negative for any x, no matter which one you pick, then the matrix P we know is positive semi-definite. And I won't go through all the proofs and stuff, but you can show that P being positive semi-definite is equivalent to the determinant of P. Right? P is a square matrix, so the determinant is well-defined. The determinant is non-negative. Here, the determinant is a scalar. And that's also equivalent to all the eigenvalues of P being non-negative. So in general, eigenvalues of a square matrix can be complex numbers, have a real part and an imaginary part. But for symmetric matrices, it turns out, for real symmetric matrices, it turns out that they're real numbers. So for a positive semi-definite matrix, you could find its eigenvalues. You could check definiteness by finding the eigenvalues of the matrix and then checking that they're all non-negative. If so, cool, you're positive semi-definite. And then a stricter version of that is what's called positive definite. So this is like a strictly positive number, sort of the generalization of that idea to a matrix. And here, basically, we have the same definition, but now we restrict the vectors x that go into the definition as saying they have to be non-zero. So not all elements of x are equal to 0. And then we get the same thing here with strict greater than signs rather than greater than or equal to. Okay. So then getting back to convexity of the quadratic form, well, if the weight matrix P is positive semi-definite, then the quadratic form is a convex function of x. And if it's positive definite, then we have what's called a strictly convex function of x, meaning that the solution is unique. So the minimizer of the quadratic function is unique. There aren't multiple solutions, there's just one. All right, so in CVX, we can program quadratic forms using either quad form or sum square. But these tend to be a little bit slow, so it can be faster to use norm instead. So just as one example, suppose that we're solving like a least squares problem, where our objective might be to minimize the sum of squares of ax minus b. So again, this is like trying to find something that is close to solving the equation ax equal to b. Maybe there's no actual solution and you want one that's sort of as close as possible. So that is equal to the 2 norm of ax minus b squared. But typically in CVX for numerical reasons, it's actually a little bit faster to minimize the norm here. So rather than minimizing the 2 norm squared, we can just minimize the 2 norm itself. And this is not exactly equivalent. There's not the exact same optimization problem, but they're equivalent in the sense that if you solve the least norm problem here, that the solution x is also the solution to the least squares problem as well. Okay, and there's some rules here, and actually I think it would be worth going through and verifying for yourself. Look back at the composition rules and the properties of convex functions and equivalent optimization problems that we talked about, and just convince yourself that these statements are true. Okay, and then what if we have a constraint on a quadratic form? We want to keep it below some level. we again can do that using the norm. And actually, I will let you guys go through this on your own, just in the interest of time. Okay, so some examples of using CVX. So let's look at a very classic one, solving a least squares problem. Okay, so here, again, we have some equation, AX equal to B, but our weight matrix probably is tall, meaning we have more equations than we have unknowns. It's an overdetermined linear system, and so there's no solution, but we want an X that comes close to solving the equation. So we have A and B. Okay, so there's an analytical solution to the least squares problem that we talked about the week before break. In MATLAB, you can get it very simply just by taking the matrix A and doing the backslash operator with the right-hand side vector B. And that's also equivalent to this set of matrix calculations. Under the hood in the backslash code, MATLAB doesn't actually form A transpose, multiply by A, calculate the inverse of that whole thing, multiply by A transpose, and then multiply by B. It does something much smarter and more efficient than that. Okay, so for a random problem instance, a pretty big one, 500 variables, 1,000 equations, we can solve this analytically in MATLAB in about 0.01 seconds on my laptop. So let's compare to the solution using sum of squares and then using norm, which I just mentioned in a couple of different slides ago here. So CVX solution, this is not the sort of right way or the most efficient way to solve a least squares problem. You should do it using the backslash operator in MATLAB. It's sort of built for that. But just as a point of comparison, how long does CVX take to solve this problem? So here we declare the variable, and then we say we have the sum of squares of AX minus B. So take all the elements of AX, subtract all the elements of B, add up the squares of all those differences, and we get the objective function. So we had 0.01 seconds for the MATLAB backslash operator and about 2 seconds for CVX. And this includes a little bit of overhead from kind of like loading the functions that CVX uses and things like that. But we get the correct answer to basically machine precision. If we use instead the norm as our objective function rather than the sum of squares, again, technically a different optimization problem, but equivalent in the sense that a solution to one gives us a solution to the other and vice versa. We cut the solve time in about half. Okay, so here for this kind of dummy problem, we're only saving about a second, so it's not that big of a deal. But imagine that you were going to solve a really large high-dimensional version of this problem that took minutes or hours to solve. Cutting your solve time by 42% might be really valuable. Or suppose that you wanted to solve a family of these problems. So maybe the same size problem that we have here, but you have 20 different problem instances and you want to solve them all quickly. So in that case, using backslash operator would save you a lot of time, but even just using the norm version rather than a sum of squares version would save you a significant amount of time. Okay, questions about this? Okay, so part of the art, the craft of being a good user of convex optimization is understanding what to do when you get bugs, when you get errors given by your modeling language, CVX or CVXPy. So suppose that we want to solve this particular problem. It's very benign looking. So we have just our same least squares problem, but we're writing it now as the norm of AX minus B, the 2 norm, squared. So back here, let's see. So the sum of squares of AX minus B, we can write as the 2 norm of AX minus B squared. Okay. So I'm just taking this form and programming it into CVX. Okay. So it looks very benign, not much going on in this problem. We know that this is a convex problem. But if we program it in this way, then CVX returns this text. So it says, discipline convex programming error. You did something illegal, something that does not match any of the composition rules that CVX knows. So we took a convex function and we raised it to the power of 2. So that's a convex function of a convex function, but that is not necessarily convex, if that makes sense, that function composition. And then it provides some suggestions of other kind of atomic CVX functions that you could use to maybe improve this. Okay, so why does this happen? Well, the square of the norm doesn't match, again, any composition rule that CVX knows, because a convex function of a convex function is not necessarily convex. So to convince yourself of that, a very simple counterexample would be, suppose you have two convex functions. One is y is equal to negative x. Right? So that's an affine function. It's just a line, therefore it is convex. And another one, take y is equal to x squared. Right? So if you take negative x and you compose it with x squared, you get negative x squared. It's a composition of two convex functions, but it ends up being negative x squared is hill-shaped, not bowl-shaped, so it is a concave function. Okay. So we need something more than just convexity. And in fact, we need a curvature property. We need the thing that we're composing with our convex function to be a non-decreasing function. So if we take CVX's suggestion of using square pos, I guess it wasn't listed here, but pow pos is the power of a positive part, which is similar to the square of the positive part. So this function is defined only basically for non-negative inputs. And so there we get sort of only the right-hand side of the square, the x squared function, which has consistent curvature and monotonicity. And so this thing here does match a composition rule because this function square of the positive part is known by CVX to be convex and non-decreasing. So when we compose it with norm, which is a convex function, we get back a convex and everything is cool. Okay, so this is a simple example, kind of a toy or a dummy example, but it illustrates again kind of where the rubber meets the road when you're trying to use these tools to do interesting stuff in your research or to solve a DER problem, something like that. And this basically is why I taught you guys a little bit about function properties and composition rules and things like that before break. All right, so that is a little bit about how to use CVX. In this next section here, I don't know if we'll get through all of it, but we will talk about under the hood. Once CVX basically takes your problem and passes it to a solver, what does that solver do algorithmically in order to actually come up with the numbers that solve your problem, or to detect that your problem is infeasible, I guess. So why do we want to learn about that? Well, strictly speaking, you don't need to know about it. So to use CVX, again, if you know a little bit about convex functions and sets, and you know the right syntax, it doesn't really matter what's happening under the hood. But knowing a little bit basically can sometimes help with debugging. So if for whatever weird reason, your problem is not solving very well, very efficiently, very accurately, you might be able to use some insights from what's happening under the hood in order to kind of tune things up. Yes, question.
How will you do that if you don't have the code behind the...
So how do you do that if you don't have the code of the solver itself, which is often the case, right? So CVX does use some open source solvers that were built basically by academics, but you can also plug it into closed source solvers, things that are made by companies. Their whole job is to make optimization solvers, right? So then how do you do debugging if you don't know what's happening, if you don't have the code that's being used for the solver? So I guess the idea here is that you might not know the exact code for the algorithm that's being implemented, but you might know sort of the structure of the algorithm, what broadly speaking, conceptually the algorithm is doing. And then you might think, oh, it's doing an inverse of some matrix. And maybe the reason that my problem is giving me a really inaccurate solution is that matrix that's being inverted is what's called ill-conditioned, meaning it has some elements that are gigantic and some other elements that are really tiny, something like this. And it might give you a clue like, oh, if I go back in and I rescale some things in my problem, maybe just with a change of units, rather than using kilowatts, I want to use gigawatts to get rid of that gigantic number in the matrix. Then maybe you find that the thing works a little bit better.
Yeah, I understand. To check your parameters if something is going wrong there.
Yeah, it's a way to sort of detect maybe where you should focus your debugging efforts. It's not going to give you probably the exact solution, but it'll give you some intuition. Yeah. Okay, so that's one reason. Another reason is they're just cool. Optimization algorithms are super useful kind of in all fields of engineering, finance, economics, etc. And they're kind of beautiful to study. And there are like a gazillion of them, and you can come up with your own algorithms for your own very specialized kind of problem classes or instances, things like that. And there's like a whole field of people who do whole graduate degrees that's just about that. So we're not going to go into super duper depth, but enough to kind of give you a flavor for some of what happens under the hood with these tools. So we'll start out, we'll get to kind of progressively more complicated optimization problems. But to begin with, let's just think about a smooth, meaning this function f, we can take derivatives or second derivatives if we want to, and unconstrained problem, meaning we don't have any constraints. So in that case, this is kind of the simplest type of optimization you can think of. So hopefully we should be able to come up with an algorithm that does this relatively well. So the optimality condition is basically just that the gradient of the objective function is equal to 0. So this is just a generalization to higher dimensions of take the derivative, set it equal to 0, the sort of calculus thing that you guys did whenever you took calc. So this is a list of n equations. So the gradient of an n-dimensional, a scalar function of n variables is an n-dimensional vector. So this would just be the list of derivative of f with respect to its first argument, second argument, third argument, all the way down the line until you get to xn. So this would be an n-dimensional vector, and this on the right-hand side is again an n-dimensional vector of zeros. So we have n unknowns, we have n equations. In principle, we can solve this thing directly. And we've talked about quadratic forms and quadratic functions a couple of times now, but kind of the canonical example of a case when you actually can solve this equation exactly is with a quadratic function. So here we have our quadratic form xpx, and then we have a linear function of x. So this is like x squared plus ax plus b, something like that for a kind of a scalar version. Okay, so the gradient of this thing, I think in one of the lectures before break, we walked through how to find the gradient of a quadratic function. It ends up just being 2 times the weight matrix P times x plus q. So this is again sort of just the vector matrix generalization of sort of a familiar quadratic plus linear plus constant function. Okay, so this is now a system of linear equations. So in general, for a non-quadratic f, we would have nonlinear equations that show up here, and those can be challenging to solve. But down here, we have linear equations, which provided the matrix P is invertible, we can solve exactly. So move the q over to the right-hand side, divide by 2, and then you'd have px equal to q over 2, negative q over 2. So if we can invert p, then we can solve that exactly. And this is the solution. All right, but what if f is not quadratic? And we end up having basically a bunch of nonlinear equations, which can be challenging to solve numerically. What do we do in that case? So the typical approach, not the only approach, but a typical one is to use what is called an iterative method. So here we would start with an initial guess in the domain of the function, but let's suppose, I guess just for simplicity, that the function is kind of all real numbers, Rn is the domain of the function. So you start with some initial guess. This is what you would give to the algorithm. Then it would run for a while. And as it's running, it would produce a series of iterates, basically better and better guesses, you would hope. So x1 improves upon x0, x2 improves upon x1, and so on. And they're all in the domain of the function. So we say that an iterative method converges if, as you take more and more and more steps, eventually you end up at an optimal solution, an x star. Okay, so one class of iterative methods are called descent methods. Not all iterative methods are descent methods. So you could have a method that, the iterates get worse for a while, but then they get much better. And eventually you converge to the optimal. But oftentimes we use a descent method. And so kind of the rough high-level structure of a descent iterative method would be, again, we're given our initial guess. At each iteration, we find a descent direction, d, and then we find a step size, alpha. And so we have a direction that we want to move in, and then you say, well, how far do you want to move in that direction? So you find both of those, and then you update the iterate. You say the new iterate is the previous one, the starting point, plus the step size times the direction. And then we just repeat. So basically all of the work in this algorithm is finding the descent direction and finding the step size. And you typically run until you get to some stopping condition. And often that would be that the norm of the gradient becomes very small. So 10 to the minus 3, 10 to the minus 6, something like that. And so why would we use this, the norm of the gradient of f being small? Why would we use that as a stopping condition in an optimization algorithm? Any thoughts? Okay. So we know that the solution to this unconstrained optimization problem, yeah, exactly. So we want the gradient to be equal to 0. And that would be true optimality. And so norm of the gradient small means that the gradient must be very close to the origin, basically.
Why would we want there? So it's one number?
So we just have one number to check, yeah, rather than having to check every element of the vector. Yeah, good point.
Close to the interior point.
Is this close to the interior point method? Basically, we're building up to the interior point method. Yeah, so this is kind of the starting point, and we'll add on. Yeah, if I get there within the next 17 minutes, 18 minutes, we will talk about interior point methods. Why do we care about interior point methods? They're widely used. They're very, very effective general purpose methods that you can throw kind of an arbitrary problem at, and it will probably do pretty well in a pretty quick amount of time. Okay, so if we want this thing to be truly be a descent method, what that basically means is that our objective value is getting smaller and smaller at each iteration. So we want x, the new iterate, xk+1, to be in the domain of the function, and we want the function value, after we take the step, alpha times the descent direction d, we want the function value to be strictly less than the current function value, meaning the thing is getting better and better by the cost function that we specified. Okay, so there are, again, kind of two components here. We want to figure out how to find a good descent direction, and we want to figure out how to find a good step size. And there are lots of choices for those two problems. And different choices and different pairings of them lead to different implementations, different algorithms for optimization. So finding a good step size, I guess, is the simpler problem. Yes, question. Oh, you were just raising your hand. Okay. Yeah, so finding a good step size is called a line search, and it's probably the simpler of the two problems. And there's a basic tension here. So okay, so you can think of optimization, at least in this kind of unconstrained case, as sort of walking around on a mountainside at night. And for whatever reason, you want to get to the bottom, the lowest point kind of in the landscape. But it's nighttime, and so it's super dark out, and so you can't see exactly where the bottom of the landscape is likely to be. And maybe all you can kind of do is feel around. You can move a little bit, and you can see, oh, well, the hillside is sloping downward in this direction. So I'll move, and that's my descent direction, right? And then the step size there would basically, the interpretation would be like, how many steps do you want to take in that direction? So if you think you're in sort of a bowl-shaped landscape, you might be able to say, okay, I'll try this way, I'll try that way. Okay, it looks like I'm moving down in this direction. But should you walk one step in that direction and then check again, or 100 steps, or a kilometer, or what, right? So if you walk too far, you'll go down for a while, but then you'll begin to go back up. And you might get so far up the other side of the canyon or whatever that you are, in fact, worse off than you began. Your elevation has risen. Yes, question.
This is also one of the closest that Mars rovers say when they're in Mars.
This is also an approach that Mars rovers take. Yeah, I mean, if you're trying to explore something, get to the highest point so that you can have a really good view of your surroundings. It's a very analogous idea. Yeah. Okay, so if we take too many steps, right? If we go too far in the descent direction, then we might end up with, if we don't go far enough, if you take a very small step, then we're going to make really, really slow progress, right? So you take a little step, and then you again kind of do a little bit of sensing to figure out where the descent is, what direction is good to move in, and then you go again, but only one step. It's just going to take forever, right? As opposed to if you go really far, and you say, okay, here's a good direction, I'm going to move a mile in that direction. Well, you might end up going back up, and being worse off than you began. Okay, so there are very sophisticated methods for solving line searches. I'm not going to give you kind of an optimal line search method, but just a quick and dirty one that works pretty well to sort of balance the trade-off between going too far or not going far enough. So basically, you run a while loop, and you say, as long as my function value at the step here, the next iterate, as long as that function value is bigger than the current function value, meaning you're getting worse, right? So that's bad. Cut the step size in half. So you went too far, right? So back off a little bit in terms of your step size. And then update, go to your next iterate. And then at the end, increase your step size a little bit from there. So by about 20% from there. And so you're progressively, as you move around in the search space, your step sizes from one iteration to the next are getting a little longer, and they're getting smaller, and then kind of repeating. And so this works pretty well. Again, not optimal, but good enough. And in your homework number 6, the last homework assignment, I'll ask you to implement an optimization method where you use this kind of simple approach to line search. Okay, so then what about finding a descent direction? Well, sort of the obvious thing to do there, not the only thing, but a good thing, is to use the gradient of your objective function in order to find basically the direction of steepest descent. So the gradient, as we know, points in the direction in which f is maximally decreasing per unit change in x. So a very famous optimization algorithm, probably the simplest to implement and very widely used. In fact, if you look at how ChatGPT is trained or some other massive AI model, under the hood, it's basically doing gradient descent. So here we use the descent direction, which is just negative gradient. And this method, you plug it in with the line search method, and you can show that it converges, meaning you eventually get to an optimal solution, for at least for a convex problem. But it's pretty slow. So its convergence rate is order 1/epsilon. So suppose you want a guarantee that your final solution is no more than epsilon suboptimal. So it's not any more than some number epsilon, 10 to the minus 3 or something like that, bigger than the best possible objective value. In that case, you would take about, let's see, 1/epsilon iterations in order to get there. So suppose that you want 10 to the minus 4 accuracy. So 1 part in 10,000. Then we need about 10,000 iterations to get that accurate. That's not such a big deal. The iterations themselves are pretty efficient, so maybe that's fine. But still, we can do a little bit better if we have a little bit more information about the function. Yes?
What about the time? So if we increase, like we go 10 minus 8, needs more time, right? And it's really complex optimization or problems. You might need like hours.
Yeah, so what if you want super high accuracy? What if you want 10 to the minus 8 here rather than 10 to the 4? Well, then you're looking at 10 to the 8 iterations, so 100 million iterations. And maybe each of them takes a second. Well, that's going to be explosive time. Yeah. So that, yeah, and if that you really need super high accuracy, or if your iterations are pretty expensive, maybe a really high dimensional problem, something like that, then yeah, you might want to look into alternative methods that are faster.
Do basic, like, you can apply that in Python, right? But do you need extra computational power in specific case? I mean, your hardware, I don't know.
Yeah, so another option, rather than getting a better algorithm, right? Another option would be to use the same algorithm, but to throw more compute power at it, right? So maybe rather than running on your laptop, you could run on a supercomputer in the cloud, right? Mm-hmm. And some algorithms, many of them are built to be parallelized, meaning on my laptop, I have 8 cores, but ChatGPT, something like that would be trained in a data center that might have thousands of computers, each of which have GPUs, graphic processing units on them that might have 100 cores or something like that. So it's solving in parallel. It's doing processing on each of those GPU processors or CPUs. And there might be a million of them, all kind of running iterations in parallel. Yeah. And so you can do both, right? You can get more efficient algorithms. You can throw more compute at it. Both find solutions. Okay, so here is an illustration of the gradient descent method on a convex problem. So these dashed lines are basically level sets of the function. So when the level sets are close together, basically means the function is quite steep. And so this is the bowl, the bottom of the function down here. So this is, a bowl-shaped thing, but kind of oblong. Steep over here, shallow over here. So we start out at x naught, and we move, the gradient of a function is always orthogonal to the level sets. So we move here, here in this kind of zigzag fashion. And we eventually get there, but it's not necessarily the most direct method. Okay, so then there's another method. I'm going to show the illustration first. I have learned that is better pedagogically. Another method called Newton's method tends to, it does more expensive iterations. There's more computing needed to compute ascent direction. But once you have it, typically you get to the kind of region of the optimum much faster. So it goes kind of in a more sane direction rather than the zigzagging. So we will talk about how to implement Newton's method. And basically, it has to do with, I guess there are many ways to approach it, but one idea is rather than taking sort of a linear approximation to our objective function and just using that first order information, what if we took a quadratic approximation? So we captured some curvature information as well. So this is basically just Taylor's theorem, a second order Taylor series expansion for a function, a scalar valued function of n variables. So here we have f hat. This is the second order Taylor approximation. Is at the point x tilde, is the function value at x tilde plus a linear term times the perturbation x minus x tilde, and then plus a quadratic term here. So this is actually a quadratic form. And the weight matrix here is this thing del squared f, which is what's called the second derivative or the Hessian matrix. So this thing here is an n by n, a square symmetric matrix. And the element ij of this matrix is just the partial derivative del fxi by del xj. So it has all the second derivatives of f in it, basically. Okay, so because this thing is a quadratic function, and we wrote down essentially the solution to a quadratic function with the general p, q, and r matrices and vectors, you can apply those definitions directly and just kind of plug in the p, the q, the r that you have up here. I won't go through all the gory details, but it turns out that we can we can minimize this quadratic function, which is a approximation to the true function we're trying to minimize. We can minimize that thing exactly. Okay, so this basically says start at this point, move in this direction, and then you get to a new point over here. So that gives us something we can use for the descent direction. So here, the blue curve is the true function that we're trying to minimize. We're sitting here at this point x tilde, and we form the quadratic approximation to f, which has shares the function value, it has the slope, and it has the same second derivative as the true function f at this point x tilde. So then our x hat basically would be the point that gives the minimum of the quadratic approximation. And then the Newton direction in this simple example would just be moved to the right, because x hat is to the right of x tilde. But in higher dimensions, it would tell you kind of more directional information. All right, so then in Newton's method, we just use that thing that showed up in the quadratic approximation, the Hessian inverse times the gradient. We use that thing as our descent direction. And then we get much faster convergence. So rather than 1 over epsilon, like we had for gradient descent, we have 1 over root epsilon here. So if you again want 10 to the minus 4 precision, now you're only looking at 100 iterations rather than the 10,000 iterations we had from gradient descent. Okay. So big improvement. And to your point, if you wanted 10 to the minus 8, it would be an even bigger improvement. Right? Okay, here's that thing I showed of Newton's method. Now we're building up to your question about interior point methods. So what if you have constraints? So all that stuff about gradient descent and Newton's method was for unconstrained problems. But what if you say, well, I want x to be below some level or something like that? What do you do there? So now we add in an arbitrary number m of convex constraints, each of which has to be non-negative. And in the first lecture on optimization, we talked about lots of ways that you can put weirder looking problems into this very general form. Okay, and then we assume that these functions are smooth and convex, the objective and all the constraint functions. So we can take derivatives of them if we want to. Okay, so an equivalent way to formulate this problem here, which has all the constraints, is to transform it into an unconstrained problem where we basically penalize any deviation of fi above 0. And we do that using what's called the indicator function, which is a way basically just to move constraints up into the objective of an optimization problem. So this thing is defined as function z. So think of z as the fi of x that we're trying to keep below 0. So if we are below 0, then this adds nothing to the objective function. It doesn't change it at all. But if we are above 0, it adds infinity to the objective function. It says, sorry, you're in an infinite amount of pain. There is no solution here. So this is just an equivalent way of writing our constrained optimization problem. So the idea behind this, what are called barrier methods, which are very closely related to interior point methods, is to approximate this thing up here and to build sort of tighter and tighter approximations to this indicator function as we progress through the algorithm. Okay, so we do that using what's called the logarithmic barrier function. So instead of the indicator up here, we put in 1 over t times the sum of each of the components of the log of the negative of f. Looks like a weird thing to do. Why would we do that? Well, basically, as t gets bigger and bigger, the log barrier function more and more closely approximates the indicator function. And so we're getting closer and closer to this version of our constrained optimization problem. So here's what that looks like. So we have z here. Again, maybe the thing we're trying to keep below 0. And then we have the indicator of z. So it's 0 over here. And then if we're at anywhere above 0, basically we have an infinitely bad, infinitely high value. So here's what the log barrier function looks like with t equal to 1. And then as we increase t, we get sort of tighter and tighter approximations to the indicator function. So if you took t is equal to 1,000, it would be basically indistinguishable from this. Okay, so then our barrier method basically just says, we're going to do an iterative method, start with some initial guess, and then we update by minimizing an unconstrained problem. And we already learned a couple of methods for that: gradient descent, Newton's method. And then this problem is an approximation of our true problem. So this generates what's called an interior point, a point that's in the inside of the feasible region, meaning all these constraints are satisfied with some slack. So they're not exactly equal to 0, they're well below 0. And then we update our step size here, the weight in our barrier function. And so t gets progressively bigger and bigger, and that means that we get better and better approximations to the true constrained optimization problem as we go. And eventually we get close to optimality. So we solve step 1 typically using Newton's method or something similar to it. Again, very efficient method. And then there's a trade-off. So if this parameter gamma, the amount by which we increase the weight t in the log barrier function, if that is bigger, then we have fewer and fewer of the sort of outer iterations. But then for solving this inner minimization problem using Newton's method, we get more and more typically of those iterations. So finding the right gamma is kind of a balance. Okay, and then we get the same basically convergence properties. That's sort of 1 over square root of epsilon convergence for barrier methods that we get for Newton's method. Okay, and then last slide here, interior point methods are basically the methods that most of the solvers that CVX uses, or CVX pi, use under the hood. Again, very general purpose, powerful methods with polynomial time guarantees on complexity. They're conceptually similar to the barrier methods that we just talked about. Some subtle details, but not too many subtle differences, rather. And then a cool thing is that when you run CVX, again, you don't need to give an initial guess. And you don't need to specify any of the derivatives, first or second order derivatives of your function. And again, we have these nice efficiency guarantees. And then even in the worst case, we're guaranteed that the runtime is upper bounded by a polynomial function of the size of your input data. Which just means even in the worst case, you're guaranteed to get basically reasonable solve times. But in practice, they're often extremely fast, unreasonably fast. And they work better basically on simpler problem classes. So we talked about linear programming as kind of a classic example of convex optimization, where you have a linear objective function and linear constraints. And in that case, interior point methods often work very fast, although there are other algorithms for linear programming that are competitive with interior point methods. And then quadratic programming, this would be a quadratic objective function with typically a linear set of constraints. And then there are weirder versions of convex optimization problems. Second order cone program. So this shows up in some norm optimization problems, and then something called semi-definite programming, which we won't talk about in this class. But the basic idea is that as the problem class gets more general and more complicated, typically the optimization algorithms run more slowly. Okay, so that's all that I'll talk about today. We'll start out with some examples of applying optimization to DER problems using CVX or CVXPy in the next lecture.